there's a theory called eternal inflation, which is a theory that, and it's actually the most popular theory, I think, at the moment, for what happened, for why the Big Bang is the way that it is. But it's got some very special features, the Big Bang, which we could talk about. But inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. And it was doubling in size in the most popular of these theories every 10 to the minus 37 seconds, which is 0.00000 with 37 noughts, 1 of a second. So it's an unimaginably fast expansion. And then the idea is that draws to a close, so it quite naturally sort of dies away and the expansion slows down. And all the energy that was taken, that was causing that expansion, sort of gets dumped into space and heats it up and makes particles, and that's what we call the Big Bang. And those theories, the slight extension to those, say that slowing down just happens in little patches. So most of the universe, the overwhelming majority of the universe, is still inflating at that insane sort of speed, and just little patches stop and they're Big Bangs. So you get multiple universes, a multiverse. It's called the inflationary multiverse, and we are in one of those bubbles, and that's one of the more popular theories.
That's another one. I mean, right now, I'm aware of what you're saying. I can sort of visualize it in some sort of a graphic form, but it's incomprehensible. Like my mind doesn't have the capacity to expand this sense of distance and size to that grasp. Is this because of just the way we evolved here on Earth to deal with the space that's in front of us, and now over the course of industrial civilization and education, we're now grasping these concepts that are so alien to the reality, the tangible reality that we exist in every day?
I'm sure that's right. Even very simple things, like you go back to the Greeks, so Aristotle and the great, very clever people, but they thought the Earth was at the centre of the universe. Why? Because it feels like it's at the centre of the universe. It feels like we're not moving. And that's quite a deep point, actually, in physics. It's like, why is it that we're flying around relative to the sun very fast at whatever speed it is, 18 miles a second or something like that, and the whole solar system is going around the Milky Way galaxy and so on? Why is it that we don't feel it? And the Greeks quite naturally said, well, because we're at the centre of the universe. They also said everything falls towards the Earth, so therefore the Earth must be at the centre. It's natural.
Right.
And actually it's quite a deep thought to understand why it doesn't feel that we're moving. You have to go all the way to Einstein, really, for someone to take that very seriously. And he said, well, this... there's a great little explanation in Stephen Hawking's Brief History of Time about this, that the idea that you can't tell whether you're moving or not demolishes the notion of absolute space. So if we think about space, if I said space to you or most people, I suppose, you'd think the way that Newton did, of a big box within which things happen. And that's a natural picture of space and the universe, isn't it? It's a thing in which all the planets and galaxies are placed. But in the Brief History of Time, Hawking says, well, imagine bouncing a ball. So we bounce a ball on the table now, a tennis ball. So I drop it and I catch it again. So let's say I drop it and it takes a second to bounce up. So in that second, the Earth has moved about 18 miles or so in space around the sun. So you could ask the question, did that ball return to the same place in space or not? And the answer is, you can't answer it. It does from our perspective, but from the perspective of someone watching the Earth go all the way around the sun, when I caught it again, it had moved 18 miles. And then from some other perspective, it would have done something else. So the point is, you can't say this is a point in space. It came back to the same place, because that just depends on your perspective. It depends on whether you're watching the Earth go around the sun or whatever it is. So Einstein said that means there's no such thing as absolute space. Which kind of follows if you think about it. But that's it's a cool but difficult thought process.
Right. I mean, that's essentially what's happening when you're on a plane. I mean, if you're throwing a ball up in the air and catching it on the plane, it's happening at a much smaller scale, right?
Yeah. I mean, you're flying at 600 miles an hour relative to the ground.
But it doesn't seem like it when you're sitting there. Yeah,
and Einstein elevated that to a principle and said, if you're moving if you're not accelerating, you're just moving at a constant speed in a plane, or now. I mean, that's essentially what we're doing now. We're moving around the sun at effectively constant speed. Then you can't tell. So there's no experiment you can do We could look at the decay of a radioactive nucleus or some electricity and magnetism or bounce a ball, have a pendulum, whatever it is. And there's no experiment you can do to tell you whether you're moving or not. Therefore, that concept has no meaning because you can't measure it. And that's led Einstein to relativity.
Wow.
So that's the basis of general relativity, which is our best theory of the universe.
Now, why is it that we think that the known universe is larger than what we can observe?
Well, one point is that it's expanding, and we always see the same radiation out there, so the glow of the Big Bang. But there are some deeper reasons. The one from the theory of inflation, the best way to explain the universe, the properties that we see, is that it's very much bigger than the piece we can see. So, for example, we measure space to be what's called flat. I don't even have to say what's called flat. It is flat. So if you imagine slices of space, let's imagine slices of them at different times. So you just slice the universe and say there's a big sheet. It's like this table.
Okay, like a table.
There's a sheet of space, and there's another sheet, another sheet. And it can have a geometry, right? It can be flat like a tabletop, or it could be curved like a sphere, or it could be curved in the opposite direction, sort of like a saddle or a bowl. And we can measure that. And when we measure it, we see it's absolutely flat. And that's a very unusual thing for it to be like. It requires, because what Einstein's theory says is that the shape of space, that the curvature of space is determined by the stuff that's in it. That's basically Einstein's theory of general relativity. Put stuff in space and it curves it and bends it and warps it and stretches it and so on. And what we find is that there's precisely the right amount of stuff in the universe to have a completely flat universe. And the explanation, the most favoured explanation for that, is the universe is way bigger than the piece we can see. And so it's like looking at a piece of the Earth. If you look at a little 1 mile square of the Earth, right, then it's flat, right? You have to look at big distances, kind of order the radius of the Earth, or not, bigger than 1 kilometre anyway, or 1 mile, to see that actually you're on a curved surface. And that's one of the ideas about the universe and why it appears to be the way that it is, because it's way, way bigger. So we're just looking at a little piece, and that's why it looks flat. And that's one of the ideas.
Now, when you say flat, like that, my brain doesn't understand this, because from our perspective, when you look up at the Milky Way, you see all these stars all over the place. So if you're saying flat, like how much height and what are you saying in terms of like the way to measure it?
The best way to think about it is not to think of 3 dimensions of space, because then we can't picture it.
Okay.
But you can think of 2, like this tabletop, and that's all right. We just forget the other one for now. And so you know what flat is on this table. I mean, you could define it. So you could say, for example, that if I draw a triangle on the top of the table, then all the angles add up to 180 degrees. So that actually defines flat. If you did that on the surface of the Earth with a big triangle, then the angles wouldn't add up to 180 degrees. Or you could draw a circle and say, what's pi? So pi is the ratio of the circumference of a circle to its diameter. That's only true on a flat surface. It's different if the surface is curved. So you can define flatness.
So when you're saying flatness, what is the height and what is the width? Like if you're talking about it as if it's a table, there must be some sort of there's a dimension to it, correct?
Oh yeah, there's a third dimension of space,
right.
But the same applies. It's just a generalization of geometry then. So you can the point is we can picture it in 2 dimensions, but you can draw. You can quite literally, you could imagine sending light beams out, and we do this measurement actually. We can look at the most distant light we can see, which is something called the cosmic microwave background radiation, which is if you imagine looking out. If you look at the Andromeda Galaxy, which we can see with the naked eye here in LA, you can see that. It's the most distant object you can see with the naked eye. And it's about 2 million light years away or so, which means the light took 2 million years to get to us. So it's a long way away, but it's very big. So as you look further out into the universe to more and more distant galaxies, you're looking further back in time, because you look at something that's 1 billion light years away, then the light took 1 billion years to get to us. So you see it as it was 1 billion years in the past. And we can actually look so far out that we can see almost back to 13.8 billion years ago, which is very close to the Big Bang. So we can look to light that began its journey before there were galaxies. And that's the oldest light in the universe, which is, by the way, one of the pieces of evidence when people say, I don't believe in the Big Bang. The answer is, well, you can see it. So it's just there. You can see it. We have pictures of it. That light, it turns out that there are sort of structures or ripples in that light, which we can use as a ruler. So quite literally as a ruler on the sky. And then because that light's been traveling through the universe, we can see how that ruler has been distorted as the light has traveled through space. And so we can infer whether space is flat or curved or how it's warps, if you like, just from that measurement. So it's a beautiful measurement.